Hello everyone, this is Melody Rondeau, and we're going to go through our second part of tests about a population mean. Our learning intention, I'm learning how to perform significance tests for population means. Our success criteria, I can perform a significance test for a population mean, and I can use T procedures to perform a significance test for paired data. So we did already start this lesson. So I'm going to be skipping around a little bit, but I'm going to also catch up some spots that we didn't quite finish, like we skipped over some things. So I'm going to fill in the holes for us. Here we go. All right, so we already talked about how to access a t-test on the calculator and about how to use data and statistics. We skipped over part A of this one, interpret the standard deviation and the standard error provided by the computer output. So this one I am going to go through and just make sure we understand how to do that. So just a reminder about standard deviation. That's the phrase that we see with standard deviation is typically varies. So we're going to throw that in here. So I'm going to start with standard deviation. And let's see. So in the context of our problem, we're looking at the width of the cubes. So I'm going to start with that. The width of the cubes. It typically varies. So there's that phrase that we see with standard deviation, typically varies. By about, and here's where I'm going to pull in that standard deviation value. I'm going to say 0.09. We see it right up there in that computer output. 0.09 millimeters from the mean. So remember, standard deviation is always a measurement from the mean. And I'm just going to make a note here. The mean there was 29.5 millimeters, and yes, I totally rounded. So there we go. So that's standard deviation. That's just a review. That's not new content, but just a reminder about how to interpret standard deviation. The other thing you're asked to interpret is standard error. So standard error is kind of based in the world of standard deviation, but it is a little bit different. So we'll see how it's different here as we write this out. So standard error is going to be if we took many samples. So remember, standard error is usually when we're doing a sampling distribution. So we have that idea of if we took many samples of size 50, just like this particular situation was a sample of size 50. The sample mean will typically vary. There's that phrase again. When we use standard deviation, or in this case standard error, we're going to see that phrase typically vary. So we'll typically vary by 0.0127. Again, I stole that from the computer output. Millimeters from the true mean. So remember, in a sampling distribution situation, we take lots of samples and we compare the means of those lots of samples to what's true, the actual true mean. And so that distance between any given sample to the true mean, we calculate all those distances and find the average. And that's where we get typically vary, and that's where we get standard error. All right, so that again was a review. That's why we skipped it in class, but I do want us to have that information and make sure you do have that filled out in your notes. All right, then we had started working on this in class. This is how far we got. We were going to do a one sample t-test, and then for our plan part, and I skipped and said, let's just jump to the do. So we got the p-value. We would be ready to conclude, but we never actually checked our conditions. So I am interested in us going through that process to check the conditions, just so we always are practicing and get this down. So I'm going to check. The first condition I'm checking is random. And if we go back to the problem, it said it is yes, because they told us it was a random sample. So that condition is met. Then I would go to my 10%. And for the 10% condition, I'm looking at, is my sample size less than 10% of the population? My sample size here was 50. And so when I apply that to this inequality, that is going to end up solving out to be 500 is less than n. And remember, our population in this case is, if you go back to the problem, it's the cubes that I believe it's produced in 1 hour. But it was cubes in 1 hour. So it is reasonable to believe that a company would create more than 500 cubes in 1 hour. So we are good there. And then finally, our normal condition, since we are doing a mean, we're looking at verifying if the true mean is the 29.5. With means, we start with that process where I start with population. In this case, no, we don't know about the population. Then I try the CLT. Is my sample size greater than or equal to 30? And yes, it is, because it is 50. So we are good at the CLT, and we're ready to do the do, which we already did in class. So I'm going to skip down to our conclusion. So for the conclude step, the first thing we do is we compare that p-value to our significance level. So my p-value was 0.23, and I'm just going to round it there and leave it at 0.23, but it does have the 2247 if you really wanted to add that. I'm going to put my box here. Remember, this box we fill in based on our alpha level. I'm going to look back. We said we were doing an alpha level of 0.05, and I believe that was because they didn't actually give us one, so we default to 0.05, and this is very clearly larger than, the p-value is larger or greater than the significance level. So then we have the decision to make. If we have a large p-value, that means we fail to reject. It means it's super likely this would just happen by chance. So we fail to reject the null hypothesis, which was that the mean equals 29.5 millimeters. And with that, we would say, if we fail to reject, we say we do not have convincing evidence for the for the alternative hypothesis, which is the thing we were trying to prove. And here I'm going to say that in words, essentially, that the true mean width of cubes this hour is different than our null hypothesis, which was the 29.5 millimeters. So remember, our alternative hypothesis was just, it doesn't equal that, so is different whether that be greater than or less than. And that finishes our conclude there. So let's take a look at, that finishes example 1. On to example 2, sorry. Example 2, come on, honey. There's the part B, sorry, apparently I missed it. There we go. Example 2, here's Fathom output for a 95% confidence interval for the true mean width of plastic ice cubes produced this hour. So this would be the confidence interval side of this. Part A, interpret the confidence interval. Would you make the same conclusion with the confidence interval as you did with the significance test in the previous example? And then we're going to practice interpreting the confidence level. All right, so interpreting the confidence interval, we should be solid at this. The first thing I do want to point out for us is where that is in our computer output. So where it says range, this right here is the interval where it has the range. So here's your lower and here's your upper. So there's our interval. All right, so we're going to jump right in. It's been a little bit. Let's review our work with confidence intervals. We are 95% confident because they told us it was 95. So 95% confidence that the interval Can't spell interval. From, and here I'm probably going to do some rounding, and just a little bit. I'm going to say from 29 point, actually there's only 3 decimals. No, that's all right. I'll put it at 2. I can't decide. All right, 29.46. The interval from 29.46 to 29.51. So I'm rounding them the same. Captures the true population mean. Oh, I'm sorry, I'm going off on population mean. I want to put it in context. I mean, which I could then put it in context, but I don't need to say population there per se. It captures the true mean width. Here's my context. That's what I'm trying to get at. True mean width of cubes produced this hour. All right, so that's my interpretation. That's the interpret part. The next part is to decide if I would draw the same conclusion. So I'm just going to squeeze that in a little bit better. So let me do that really quick. Cubes produce this hour. Okay, so then we want to know, does our interval suggest the same conclusion? If we look at the interval, we're basically looking at, is our value for the mean. So I'm going to go back so we can see that really quickly. We were looking at the mu equal to 29.5. You can see it in our state step there. Is that in the interval and it looks like it is. It is within the interval. So fantastic. So from there, the interval does capture the true mean. So I'm going to say something like that. I'm going to say since 29.5 is in the interval, it is a plausible value. Remember, that's kind of the point of the confidence interval, is to not only estimate the true mean, but to give what would be plausible values for that particular parameter. Sorry, plausible value. For the mean width of cubes. In other words, we are making the same conclusion that we had before. Mean width of cubes, which in both cases we are sticking with the 29.5 as a reasonable answer. On the other one, we failed to reject the null hypothesis. I'm going to go back so we can see that. We failed to reject the null hypothesis, meaning we did not have evidence to say it was something different than 29.5, so we're sticking with the 29.5. So I'm just going to say that we would make the same conclusion. Cool. All right, so that's part A. Then we have part B. Interpret the confidence level. We haven't done this since we did confidence intervals. So this is, again, one of those review things, just for the review. And a confidence level is if we took many samples. So here we go with that phrase again. If we took many samples, or you could even say if we use this procedure many times, this of creating our confidence interval. So if we use the same process many times, but I'm going to say if we took many samples of size 50, so I'm basically describing the procedure. And remember that 50 is cubes produced this hour. and constructed confidence intervals in the same way. So if we do that process over and over again, this is where that 95 comes in. I missed the word about 95% of our intervals should capture the true mean width of cubes. So that's what the 95% is. If we did it a bunch of times, then the intervals we create, 95% of those intervals would capture the true mean width of cubes. So I'm going to say that about 95% of the intervals would capture the true mean width of cubes. Cool. A lot of writing, but again, nice review back from our confidence intervals. And remember that 95% is not a probability of capturing the true proportion. It is the percentage of intervals that actually do it when we build them out. So I want to keep that straight. All right, then moving on to the last piece, and this piece is the important part that we didn't quite make it to. So make sure you're definitely getting the notes here. Paired data. Our paired data is data from two observations on the same individual or one observation on two similar individuals. So typically this would be, this is related to like a matched pairs design where you're comparing either the same person doing two different treatments and seeing the effect, or possibly two different people but very similar, or two different objects very similar, that you're comparing the two effects of this particular thing. All right, so paired T procedures. If conditions are met, we can use one sample T procedures. So even though we're looking at two, what we might call two different observations or treatments or things here, we're going to put them together into a single problem, and so it's going to still act as one sample. So one sample T procedures to perform inference about the mean difference. So we literally are comparing them by finding the difference. To see what that means, let's take a look. All right, example 3. For their second semester project in AP Statistics, Libby and Catherine decided to investigate which line was faster in a supermarket, the express lane or a regular lane. To collect their data, they randomly selected 15 times during a week, went to the same store and bought the same item. One of the students used the express lane and the other used the closest regular lane. To decide which lane each of them would use, they flipped a coin. They entered the lanes at the same time, paid with the same method, and recorded the time in seconds it took them to complete the transaction. Carry out a test to see if there is convincing evidence that the express lane is faster on average. All right, so this one is going to be tricky because we want to know that last part, if the express lane is faster. So this one, I feel like it's helpful to actually try and write our hypotheses first. So what is it we are assuming to be true? And it says on average, so we know we're dealing with an average. And I'm comparing two different lanes. I have the regular lane and the express lane. And so actually I'm going to write this over here. So I'm going to say D equals, I'm doing the regular minus the express lane. Okay, so I'm seeing if I set that up, when I do a comparison, remember we did this a while ago where we do a subtraction. So it's going to be regular minus express lane. If the regular is faster, then if the regular is faster, that means it's actually less time. I'm sorry, I want the express lane to be faster, excuse me. If the express lane is faster, it's going to be less time. So this one is going to be a lesser number, and the regular lane would be a larger number. So this is less and this is bigger. So if I take that and think about numbers there, if I do a bigger number minus a smaller number, my answer is going to be a positive number or greater than 0. So this is going to help me to write my hypotheses. This is what I'm trying to prove, so that's going to actually be my alternative. So I started to write my null hypothesis. I'm going to skip over to the alternative for a minute and say, okay, I want the mean difference to be greater than 0. So if that's the case, what is the expectation that's true, or that we believe to be true before starting this out, before proving it? The expectation, or what we think is true, is that it doesn't matter which lane you go in, that it's the same. So if I go back to my thing here where I said big and less, if those are the same, if I do r minus e and it doesn't matter, it's the same, then my difference would be 0. So the null hypothesis is basically that it doesn't matter, or there's no change or no difference. Or we would say m, the mean of the difference, is 0. So hopefully that works and you guys get that. If not, we can ask questions when I'm back with you. All right, so we're going to start with our state. We want to test the hypotheses, and I'm just going to say above because I already wrote them, where the mean of the difference, so MD, is the true mean difference and I'm just going to clarify, when you do this, you do need to clarify what you're subtracting. So I'm going to say regular minus express, because that's the equation that I set up at the beginning. The true mean difference in checkout times. And so that's basically my setup. So we want to test the hypotheses. I have the hypotheses listed. Normally I would put them in, but since we just wrote them, I left it. I defined my variable, and the last thing is at what level of significance. They did not, I don't think they gave me a significance level, so I'm going to say at alpha equals 0.05 significance level. All right, so that's my state. Then when I go to my plan, here's where it may be, so far it should be based mostly the same, a little bit in terms of the setup. My plan here is that I'm doing a paired t-test because I had two things that I'm kind of comparing to each other, which one's faster or slower, so I'm putting them together into this idea of the mean difference. That's called a paired t-test. And when I check my conditions, because I am going to still check the conditions, I have the same basic set of conditions. Was it random? And so my answer there is yes, it was random. They randomly selected who went to what lane. They even randomly selected what time of day they went. So yes, we're good on the random. My 10% condition, I'm looking at n is not greater than, n is less than 10% of n. So here it said they selected 15 times during the week. So when I solve out this inequality, well, if I solve it correctly, that would help. I get 150n, and this, my population though is going to be that, because up here it said 15 times during a week, this n is times during a week. And just to clarify, we're not exactly sure how they're getting their times during the week, if they're like putting in like every 5 minutes or every 2 minutes, but I think we can argue that there's more than enough time for it to be more than 150 times during a week that could get chosen. So I think we're good there. The last one is going to be our normal. And when we go to check normal, we're looking at the population for the checkout times. They didn't tell us anything about the shape of the distribution of the population, so no. My CLT, I'm looking for n to be greater than or equal to 30. It is not. greater than or equal to 30. So then I have to go and look at the graph, which we don't have handy. So here comes the fun part. When you are going to put this in, because I just kind of jumped into the problem, so what you would actually put into your calculator from this problem is we have the times for regular and express, but what we're interested in is the difference. So this column that I just put the arrow there, that's what you're going to enter into your calculator. So go ahead and do that. Maybe pause the video and come back, and I'm going to pull over so we can see what that looks like. So I actually pre-did it. Here it is. I put in my data. This is lane difference, or difference between regular minus express. Maybe I should call it that. But I put in all those difference of times, including the negatives. And then once I have that, I can, of course, run my stats. So I'm going to hit Menu, Statistics, Stat Calculations, and I'm doing one variable statistics because I'm just looking at the difference. I have one list. I'm going to choose my lane difference, and I'm going to make sure it's in a different column for my results, and that gives me my statistics. Also, because specifically right now I'm looking to graph this, I'm going to grab my data and statistics. I'm going to do Control Doc, add a page. I'm going to add data and statistics, and then I'm going to put in lane difference. And you can see here, since I had some negative values, I start in the negatives, but I go across. And this one does seem to be like an outlier. And so this would be a place where I might actually say, that's too much of an outlier. This would be a thing where you would definitely draw attention to that. However, because I want us to practice those T procedures, we're going to do it anyways and pretend that it's not really an outlier and that we're good. But here's a case where I would say, that's pretty significant outlier-ish. We might consider not doing the procedures, but of course, because we're doing it in class, we're going to do it anyways, so we can see the process. So in terms of our conditions, I don't know why it won't let me floof that. Let me see. Hold on. Come back to my floofer flaffer. There we go. Okay, so in terms of the conditions, we're going to say, yep, we met the graph, even though it is perhaps a little sketchy there with that outlier situation. So here we go. But I am going to say yes, and there we go. So let's go ahead and go forward and see what the do step is going to look like, because that's going to be where we see that it's very much the same as what we did before. So here goes with my do step. All right, so I'm trying to find my T test statistic, and that's going to be, typically it's X bar minus the mean, and it will be X bar minus the mean, but we're going to tag on the difference because this is done as a paired t-test, so it's in terms of the difference between the two different things we were looking at. And this would be the standard deviation of X bar, the difference. That's a nice little chain there. All right, so here's where we're definitely going to need that calculator data because I don't know what the mean of the difference is unless I go back to here where I have it in my calculator, 43.2667. All right, so I might just round this though to 43.27. So let me do that. All right, so 43.27. The mean of the difference, whoa, go away, honey. All right, the mean of the difference was 0. That's from our null hypothesis. And then we need the standard deviation, and remember we are going to be dividing by the square root of n, which is 50, but I have to pop back to my calculator in order to find that standard deviation. So back over here, there it is. Remember I have to do the S version, not the sigma, but the regular S here because it was a sample, 83.92. I'm going to call that 83.92. So I'll put that in, 83.92, and then I would calculate all of that, and when I'm done I get 1.997. And just a quick picture draw here of what that looks like on the t-curve. There's my middle. I have t equals 1.997. The area here is what I would look up on the table, or that's what I would get from the table, is the area or the probability there. Quickly, in order to do that, I would need degrees of freedom, n minus 1. In this case, that's going to be not 14, dear heavens. Oh yes, 14. I'm sorry, this is weird because it is, sorry, I was thinking we were doing the previous example, which was 50, and I gotta fix my thing there. Whoops, I apologize. Should not be 50. Our sample, there were 15 paired up times, so 15 values that we put in. I apologize. It's still, the 1.997 is correct. I just, sorry, got ahead of myself there. I don't know where 50 came from. I think that was the last example. It should be 15. And then my degrees of freedom should be 14 here. Again, you can look this up on the t-table, but I like to use the calculator because I feel like it gives more precise on this one, better answer. So just quickly on how I would type that into my calculator, I would say I'm going to start at the 1.997. I'm going to go up to what would be infinity. I just type in 10,000, and then my degrees of freedom is 14. That pops out with a 0.0328 and then 23. And remember, this right here is your p-value. So that's what we're going to use in our conclusion. And we are there, people. Here we go with the conclude. So I have the p-value equals 0.032, I'm just going to say 0.033, I think, round it off a little bit, just to make this a little bit easier. Cool. And then here's the box I'm going to fill in a minute. My alpha was 0.05 equal to alpha. And then I need to decide which one is greater than or less than. In this case, it looks like we are less than. And when we have a small p-value, we reject the null hypothesis. So in this case, we reject H naught, that the mean difference equals 0. So we get to reject, hooray. I'm going to just squish this together a little bit so if it's just a little bit nicer. So here we go. We reject. All right, and if we are, well, I'm trying to get this straight. If we reject the null, that means we have convincing evidence. We have convincing evidence that the true mean difference, remember we did all this in terms of the difference, the true mean difference in checkout times and our checkout times were the regular minus the express. The true mean difference is greater than, was it greater than? Sorry, I got to go back and look. What was our null hypothesis? Was that the difference was greater than, okay. That was because the regular should be longer than the express, so yes, is greater than 0. And I think this was done in seconds, so I could say 0 seconds. Meaning, here's where I'm tagging on what that means, because in this case, the 0 doesn't really help us make that decision, doesn't help someone reading it to understand perhaps that the regular is longer and the express is faster, so I'm just going to actually say that, meaning the express lane is faster. All right, that, I believe, finishes those notes. Nope, I lied to you a little bit, only a little bit. If we go forward, there's a little bit more. I don't think there's more for you to write, but there's some things for us to read through. So using tests wisely, significance level is basically, remember, that's the risk of a type 1 error, or the probability for a type 1 error. And so how much are we willing to accept? If making a type 1 error which means rejecting the null hypothesis when it's true. If that will have a significant consequence, we might choose a smaller alpha, since a low significance level lowers our chance of making a type 1 error. Otherwise, we use 0.05 or 0.10. Since increasing significance level decreases the chance for type 2 error and increases our power. So sometimes you'll see, even though our default is 0.5, the next most common will be the 0.10 because it increases the power of our test. Effect size, the difference between the null parameter value and the actual parameter value, that's called the effect size, how different those are. And how much difference is important for us to detect, that depends. The power, going back to power, is the probability that our study will detect a difference for a specific effect size. So how large does this probability need to be? That changes depending on our situation. Don't stress too much about that last part. All right, so determining sample size. Sorry, went a little ahead there. When you choose a smaller significance level, such as 1% rather than 5, you have to take a larger sample. So when you use a lower significance, or a lower significance, you need a larger sample. Smaller significance levels require stronger evidence to reject the null. So we have to have basically more proof. And remember, larger samples give us more proof. If you insist on high power, such as 0.99 rather than just 0.9, so a higher power, you also need a larger sample. Higher power gives a better chance of detecting a true difference from the null hypothesis. And then at any significance level and desired power, detecting a small difference between the null and alternative values requires a larger sample size. So basically, larger sample size is pretty much always our go-to. And statistical significance is not the same as practical importance. In other words, you can find something to be statistically significant, but it doesn't matter in the real world. It happens to be a statistical find, but doesn't actually affect anything. So that's something to keep in mind too. All right, let's take a look at this last one. I'm sorry, I forgot there was one more about the superintendent. So the superintendent of a large school district wants to buy a computer-based math program for his district. Because the program is very expensive, he will randomly select some classes to pilot the test program. Oh, to pilot test the program, excuse me. The response variable will be the average increase in grade level equivalent for the students in the class. For example, a student went from 3.1 third grade 1 month to 4.3 fourth grade 3 months by the end of the school year. The student increased 1.2 grade levels during the year. The hypotheses that the superintendent will test are: the null hypothesis is mu equals 1, and the alternative is mu is greater than 1, where mu equals the true mean increase in grade level equivalent for classes in the district. To determine the number of classes he should use, the superintendent considers the following. All right, so looking at basically how does this work out in the real world when we're talking about what kind of sample do I need in order to get what I'm looking for. So significance level. The superintendent wants to avoid a type 1 error, so what significance level should he use? A lesser value for alpha, so we are less likely to spend money on a program that doesn't help. So this gives us the question, and I gave us the answer. So we want a small value for alpha, so we don't spend money on a program that doesn't actually work. Then the effect size, what amount of increase is important to detect? How much are we hoping that actually shows us an increase? Like a little increase is probably going to happen anyway, so what kind of increase are we looking for? In this case, a mean increase of 1 month, or 1.1 is what we're looking for. And the power, if the superintendent wants a power of at least 80.08, what does this mean in context? It means there's a probability of at least 0.8 that the test will detect an increase of 1 month in grade level equivalent growth. All right, so that a lot of information there at the end, but that does wrap up our notes. I'm going to end out our slideshow here, and I will be back with you guys soon. And happy working on notes and reviews and all the good stuff.